Alright, so our second half of our lesson on parametric equations it's a good one. We're going to be developing more equations, so that's the focus of this part of the lesson. And the notes actually start with a warm-up question of what we did on the previous lesson. So if you don't mind, I'm going to skip this one because they're a little tedious. In fact, I just was keying up the book assignment and I was just feeling awful because, you know, it's not that it's difficult for you guys to plot points, but it's just so tedious because you have to sit there and plot all these different points and then make this parametric curve. So I apologize in advance for your last homework assignment. And then this problem here, I'm just going to, if you don't mind, I'm going to skip it because it's really just warming up from the previous lesson. Alright, so what we're going to think about today is how we can create rectangular form with theta as a parameter. So theta referring to a trigonometric angle typically. And we have to go back and think about our trig traits. So this example here is already done for you. And they started off with the parametric equations of x equals 2 cosine theta and y equals 4 sine theta. So real basic parametric equations that we're given. But what they're going to do is they're going to, get my board to work, here we go. They're going to isolate the theta, well, not quite the theta, they're going to isolate, I'm going to say this. Okay, we're going to rewrite the parametric equations in terms of the Pythagorean identity that we know of. So if I can isolate the cosine and sine functions, that's what we want to isolate. That was their first step. So they're going to divide by 2 here and here. And that's how they got cosine theta is really x over 2. And then over here, they're going to divide by 4. So sine theta is really y over 4. So then they take those two clues and they take the fractions x over 2 and y over 4, and instead of cosine and sine for this Pythagorean identity, they replaced cosine and sine with x over 2 and y over 4. So then they square the fractions and they get x squared over 4 plus y squared over 16 equals 1. And what do you know? That is one of our conics. So isn't that nice? We're just kind of marrying various things we've learned in the past. This is an ellipse. So if we're going to graph this ellipse, we're going to see that the minor axis in the x direction is 2 units. And if you remember, I'm super awesome at graphing ellipses, right? Center was at 0, 0. I forgot to write that. The major axis is 4 in the y direction. And I'm totally going to kill this, right? Here we go. Oh, wonky. Okay. So, yeah, totally awesome. Yeah. You know what? I'm going to call that a win. So we just took our parametric equations that were in, well, obviously parametric form, but they were in terms of the variable theta. We used some trig, and then we ended up with a very cool conic, and that would be us graphing it in rectangular form. So here in your notes, very similar questions. We're going to have to solve for sine and cosine. So if I rearrange this equation, sine theta is x over 3. And then rearranging this equation, cosine of theta is y over 2. So again, using our Pythagorean Pythagorean identity, sine squared plus cosine squared would be x squared over 9. Squaring this would be y squared over 4 equals 1. And write each pair in rectangular form. I think I'm done. That's all they wanted. That wasn't too bad at all, was it? Alright, this next one I can't see, so let's move this out of the way. So very similar. Sine would be y over 4. And cosine would be x over 5. What a fun way to end our unit on conics. Alright, so Pythagorean triple, cosine squared plus sine squared, any order, does not matter. I'm going to put the larger axis, the major axis first. So that gives us x squared over 25 plus y squared over 16 equals 1. But of course, commutative property, we can put those terms in any order you want. Old habits die hard for me, and I always put the major axis first on an ellipse. I say always. I try to always put major axis first. Alright, so here we have, what do they want us to do here? They want us, oh, this is fun. We're going to use the sketch and then create the inverse, huh? So, They want us to sketch the graph and also the inverse itself. This parameter for x and this parameter for y we can do in our first parametric equation. And then what I would do is remember something about inverses, huh? Don't x and y just switch? So for the inverse, the x parameter is going to be t squared plus t, and the y parameter will be 3t minus 1. So if we go ahead and do that, and then it says to set up your window accordingly, do a zoom square. Alright, go ahead and pause the video. I'm going to pause mine as well. I'm going to get everything typed in. Alright, so I have 2 sets of parameter equations typed in here. Let me go change my graphing method though. I have that bouncy ball option still. Let's get the regular graph. Doesn't really matter, but that works for me. Alright, okay. So function and the inverse are typed into both sets of parameters, and then I went to window. I set up my t's to go from -10 to 10. Right now it's t stepping as 0.1 just to make it smooth, and then I'm going to go to zoom and then choose square, which is number 5. That's beautiful. And remember, inverses are reflections across the line y equals x, which would be a little difficult still here, but that line right there. So these definitely see the properties of inverses. So go ahead and sketch that on your paper as well. So going back to our lesson, there's a question right after it that is very similar. So same thing, x and y parameters we'd plot, and then for the inverse we just switch them. So nothing too exciting. If we flip the worksheet over, I think we're going to start to hit some more application questions. So what I want to practice is us creating these equations, because that's usually what happens with applications, is they don't give us the equation and we have to create it. Now, this one in particular, they want us to graph and represent the situation of a ball being thrown with an initial velocity of 90 feet per second from a height of 5 feet. They've already given you the parameters and they already told you what to set up for the window. The only thing that's kind of unique and new is they want you to plot 2 parametrics at the same time, but then they will also want you to play around with the option for what the graph looks like, and we saw that on the previous question. So if you go back here and you go to line options, this one is going to look like a ball, and then it like shows like a comet tail after it so you can see the path, and then this one is just literally looks like a ball flying through the air. So that's kind of cool. Technology and all that looks pretty neat. If you're working on an older calculator, you can find it in the same spot where you go behind the y equals. It just looks a little different obviously on the non-color screen. So I'm going to skip. This ladybug question is kind of cute because it's about a ladybug walking back and forth on a line, but we're going to skip it because there's not a lot of point to it. This is what we have to get to. So from yesterday, an object being launched, remember, has a horizontal position parametric that looks like this. T times initial velocity times cosine of the angle at which it's launched. And then the vertical position parametric equation looks like this. So gravity, so -16t squared. And this is gravity measured, remember, in feet per second squared, acceleration due to gravity. If it's in meters, we have to think about that. We convert something. Plus t times initial velocity times the sine of the angle plus the initial position or the initial height. So let's see one of these questions in action. If I could actually see it. We're modeling a rocket. Rocketry. I don't think I've ever heard that word. Alright, so we have initial velocity of 80 feet per second. So that's your initial velocity. Angle of 80 degrees, so that's our theta. Did I cover up half the problem? No. Alright, so it says write the parametric equations. Sure will. Alright, let's start with our horizontal position parametric equation. That formula. And order doesn't matter, remember, because you're just multiplying. So I usually say t times initial velocity, which is 80, times the cosine of, also happens to be 80. It's coincidental that those numbers match, but make a note that 80 degrees, that's the theta. Because that's not always going to be the same, is it? And then for our vertical position parametric equation, we're going to use the formula -16 t squared plus t times our initial velocity times the sine of 80 plus, and it's launched from the ground, so there's 0 here. So they want me to answer some questions now, and I am going to get these graphed in the calculator, so I'm going to pause my video, you pause your video, let's get everything typed into our first parametric equation setup. So I have our equations typed in. On my original notes on my key, I changed like the initial velocity to 70, so I don't know if we just did that for fun, just to change up the problem a little bit, but either way, we do have to set up our window. And T represents time, and we're launching a rocket, so I kind of was a little generous with some of my window extremes. I went from 0 to 30 for time. For horizontal position, again, it's a rocket, so I went like to 100. And then same thing for the height position function, I went to 100 for that as well. So when I hit graph, there we are. So the first question says, how long will it take the rocket to travel 10 feet horizontally from its starting point? So basically I want to know when x equals 10. And if you hit trace, like with our curve, and I try typing 10, remember that's t is going to pop up, right? Not our x. So maybe a better option for us would be to go to our table. And then we're going to have to kind of like estimate it, but I see that the horizontal position would hit 10 like between 0.7 and 0.8. And really pretty close to 0.7. So I'm going to say that as an answer, like roughly 0.7 seconds. And then the next question says, what is the max height that is reached and how far away does it land? So for here, you can either play around with the table or you could trace along your curve. The max height we can get to pretty easily, even with my slow calculator. Oops. Delay. Okay, there we go. So it's, it's an estimate, but I'm seeing a max height of around 97 feet. And how far out is it right now? It's 33.3 feet away from the launch site. And if you're curious at what time that occurs, I can see t equals 2.4 at the bottom of the screen there. And then how far away does it land? Well, I gotta figure that out by going over here. Trace it along. My lag on the calculator. Oh, back up. I always forget about that delay. There we go. So how far away? Like 68-ish feet away from the launch site. That's what they're looking for, huh? Alright, so on my key, on my notes, I changed the parametric equations, so you might see different answers there. But for our problem, these are good answers. So that's how we're going to answer follow-up questions to these. So can you write an equation? That's my first question. Can you figure out your window so that it's appropriate? And then can you further answer questions based on scrolling along your graph or maybe looking at your table? Alright, I'm going to stop the lesson there. The next question is about a drive on a golf range, driving range. And it's a cool problem. It's a neat parametric equation set, but it's pretty much the same. So best wishes to you.